No, where? 4?
Yeah.
Fourth derivative, add 0 was 1, right? So we get 1 over 4 factorial x to the 4th. So maybe that's enough. I'm going to kill off the things that are zeros. Those are zeros because there are zeros in the numerator, right? So they're gone. And then what about this one? Well, I can leave it like this. 1 over 0 factorial x to the 0, excuse me, minus a half, or sorry, 1 over 2 factorial x squared plus a fourth, wow, I said it again. 1 over 4 factorial x to the 4th plus dot, dot, dot. That's what we have left. And now I write this as sum, n equals 0 to infinity. Okay, starting with n being 0, I alternate, right? Again, I alternate, starting with a positive. So I'm going to get that with the negative 1 to the n, right? Not n plus 1. And then I'm dividing that by, what? 0, 2, 4, 6, 8. So it'll be just even numbers. So just 2. Will 2n work? 2, careful, 2n. Yeah, will this work? Yeah, because you want what first? 0 factorial, right? So 2n in parentheses factorial, right? You plug in 0 to this, you get 0. You plug in 1, you get 2. You plug in 2, you get 4. You plug in 3, you get 6. And then over here, x to what power? 2n. There it is. That's the Maclaurin series for cosine. Now, I haven't shown you this. I'll show it to you now. So this is the graph of cosine. This is the graph of cosine. And what I'm going to do here, maybe, if it's going to work for me here. For some reason, that's not. Let me read. Okay, there we go. So what I'd like to do here is just so you can see this. What is this first term right here? What is that for real?
1.
That's just 1. So it's 1 and then minus. This next one is x squared over 2. Then plus the next one is x to the 4th over 4 factorial is 24, right? And then it would be, the next one would be minus, wouldn't it? And then something, okay. What I have graphed right there, the red is cosine, right? The red is cosine. The black line that you see right there, right now I'm only graphing the first term of this series. And so what we're saying is we're approximating the cosine function with just 1. We did this in class. Remember I was telling you, like in a physics class, they'll tell you if you want to approximate cosine near 0, just use 1 minus x squared over 2. Okay? So if you just use 1, it's not a very good approximation. But now I'm going to do 1 minus x squared over 2. There it is right there. See it? That's better, right? Now let me add more of these. And watch what happens as I add more. I've shown you all this already, but just to show you that when it comes to this, for the Maclaurin series for this cosine function, its radius of convergence is infinity. Basically, it's defined everywhere. So you never really technically need to shift it, because if you go out far enough, it basically becomes the cosine function. Now, you might want to shift it if you were looking further down the line, you wanted to approximate something further down, you could shift it just to make it happen faster. So you don't have to go out like 1,000 terms for it to match. Does that kind of make sense? Like right now, the black one is only really valid in that little window between -10 and 10, right? If you were way out at like 100 and you wanted to mess with the function out there, then you would need to go a lot further. And so it'd be better just to shift your black region to the right, and then it would match over there. Does that make sense now a little bit? Like what the difference between Taylor and Maclaurin is? Maclaurin is you're centering that black right there at the center. Taylor allows you to move it around, okay? All right, sine does that was cosine. Sine does the same thing. E to the x, same thing. And on that sheet, doesn't it say the radius of convergence? That sheet that's printed sideways? Sorry, the one that On the sheet that you can get online, it'll show you on the side the radius of convergence. And if it says infinity, that means that that's valid everywhere. All right, next example. Find the Maclaurin series for x squared cosine x. Okay, wait a minute now. Pardon? Yeah, there's an x squared there. Okay. This is where things get bumpy. Everything's worked out pretty clean up to this point. But we want to be able to find the Maclaurin series for any function, right? Not just the easy ones, e to the x, sine x, cosine x. So what I'm going to do is I'm going to start making a table, all right? And so I'm going to have the derivative right here, the zeroth derivative. Well, let's start with that. Zeroth derivative is x squared cosine x, right? Okay, let's get the first derivative. The first derivative of this, you're going to have to do what? Product rule. You're going to have to do a product rule. There's a product right here, right? So it's the derivative of the first one times the second plus the derivative of the second one. What's the derivative of the second one? Negative sine, so I'm going to put minus, and then it'll be, I'll go ahead and write it. It's sine x times x squared. Okay, but what's that equal to? Let me just clean it up a little bit. It's 2x cosine x minus x squared sine x. All right, that's what we have. Shit, man. That's only the first derivative. Now we need the second derivative. So when we take the second derivative, when I look at this right here, right, I have two terms. I can differentiate them individually, but each one of them is a product rule. I know, right? So let me do this one. First, let's do that product rule. Derivative of 2x is 2 times the second one. Right? Derivative of that one times that one. Then plus, what's derivative of this one? Negative sine x times what? 2x. I'm going to put the 2x in front. That's just the derivative of this, right? Okay, minus, I'm going to put the minus and I'm going to put parentheses, because I now need to do the product rule on this, don't I? Yes. Shit, man. Right? So 2x sine x, that's the derivative of the first one times the second, plus, now derivative of the second one, cosine x times x squared. This is getting bad, isn't it? Really quick. Let me clean up though, hold on. I'll get the third one in a second. 2 cosine x minus 2x sine x minus 2x sine x again, right? And then minus x squared cosine x. Do y'all agree with that? All I did was distributed this negative through. Yeah, this isn't e to the x anymore, is it? Right? This is something more complicated. All right, this is equal to 2 cosine x minus, what is that, 4x sine x? Those are like terms, right? I can put this one and this one together. And then we have minus x squared cosine x. Shit, man, this is terrible. We're supposed to come up with a formula for the nth derivative? Are you kidding me? Right? Is there a question? What's up?
Isn't that plus x squared cosine x?
Plus. Oh, where?
Because you took the derivative of sine for the second line, right?
Wait, which one are we talking about? From
on line 2, the cosine x should be negative.
right here?
Inside the parentheses, right?
This one?
Yeah, because you took the derivative of the sine.
I was doing this, right? I was doing product rule on that. Here's the minus right there.
Yeah.
Derivative of that is this times this plus Now derivative of sine. What's derivative of sine? I think you're thinking antiderivative,
Oh, maybe. My bad.
right? Derivative of sine is cosine and then times the first one.
Never mind.
You're probably just thinking anti.
Yeah. We've done so much.
I know, right? I know. It's like here we get to go the other way again now. And then I distributed the negative through, right? So are we okay with this being our second derivative? Shit. Okay, let's try for the third. The third, let me separate these. That's my second derivative. My first derivative's there. My 0th derivative's there. Okay. So to do the third derivative, well, I can do that one. That one's pretty straightforward, right? Negative 2 sine x. And then, oh man, product minus parenthesis, here's my product. 4 sine x plus 4x cosine x. I'm doing product rule right here. And then minus, right? Minus, now I take derivative of that. That's another product rule, isn't it? But this is what we have to see. This x squared cosine x, forget the minus. That x squared cosine x right there is something we already did. And what was that? What was the derivative of that? This right there. So I'm not going to have to do that derivative again. I'm just going to copy that down. So this is going to be 2x cosine x minus x squared sine x. All right, let me distribute and clean up. Double check my work there. Does that look right to you? Combine like terms. I have negative 6 sine x, right? Minus 6x cosine x, and then plus x squared sine x. There's this theme in math, right? Anytime something gets hard, then we get this shortcut that makes it easier, right? And then it gets hard again. And then we get a shortcut that makes it easier, right? So we got this thing, Maclaurin, right? It's going to make our lives easier by letting us look at functions a different way. And then you start looking at some complicated ones, and now it's getting harder again, right? And there's going to be a way around this in a minute, all right? Okay, but we got to grind this out. Here we go. I've got to go until I can find a formula, like a generic formula for this. So what about one more derivative? Let's try the fourth derivative. Fourth derivative. The fourth derivative here. All right. Derivative of that one. Negative 6 cosine x, right? And then another product rule. Minus, here we go. So forget that minus. I'm doing a product right there. So what is it? 6 cosine x plus, but then a minus, right? Right, a plus, but then the derivative of cosine is negative sine. So minus 6x sine x. Look, I'm doing product rules, right? At the end of the day, I'm just doing product rules, which you all want to pass Cal 2, right? So you should be able to do product rules. Right? I know I'm going fast through them, but all right, now what? Plus the derivative of this one, right? Did we ever do that? Did we ever do that? We did. Right here. Wasn't it right here? We did it. That was right there, and we did that work, and isn't that this line right here? Or this piece? Right? It's just product rule. So I'm going to just copy that. And do I need it in parentheses? Technically, I don't, because it's a plus here, right? So derivative of this is just going to be 2x sine x, and then plus x squared cosine x. Hey, x squared cosine x. I saw that earlier, didn't I? There is a pattern starting to appear here. Because I'm going to have to differentiate that again, right? Okay, but let's clean up the rest. This is negative 6 cosine x minus 6 cosine x plus 6x sine x plus 2x sine x, right? And then plus x squared cosine x. And cleaning that up, that's minus 12 cosine x plus 6x sine x. Oh, wait, no. 8 plus 8x sine x plus x squared cosine x. That's my fourth derivative. I'm going to do one more to see if we can finally come to a pattern. The fifth derivative is going to be 12 sine x, that's derivative of this, plus 8 sine x plus 8x cosine x. That's my product rule right here. Yeah?
Yes.
Plus, okay, derivative of x squared cosine x. I did that in the very beginning. And that was this one right here. So 2x cosine x minus x squared sine x. What a monster. All right, this is going to be 20 sine x plus 10 x cosine x minus x squared sine x. Let's just see if we could guess what the nth one is. Let me box the ones that are our answers. Let me box our answers. So here's the 0th derivative. Here's the first derivative. Here's the second derivative. Here's the third derivative. Here's the fourth derivative. And here's the fifth derivative. Okay. Let's look at all the even ones first. Even derivatives. Even meaning 0, 2, and 4. What do they all have in common? 0, 2, and the 4. They all have x squared cosine x, don't they? X squared cosine x, then minus x squared cosine x, then what? Plus x squared cosine x, right? They all have that alternating happening with the x squared cosine x. What about the stuff in front? So look at the evens. Here it's by itself, right? And then all of a sudden we get what? 2 cosines to appear, then minus 4x sine x. What is the next one? Minus 12 cosine x's, and then 8 of these. And then that. I feel like maybe we need another one. Do you feel like we need another one? Does anyone see a pattern? Let me do another one fast. This will be what? 20 cosine x plus 10 cosine x minus 10x sine x minus, and then this right here becomes derivative of that. 2x sine x plus x squared cosine x. Cleaning up, I'm going to have 30 cosine x, that's those two together, minus 10 of these, minus 2 of these, so minus 12 x sine x, and then minus x squared cosine x.
I'm noticing all the terms are at least alternating.
Okay, so yeah, you want to look at the cosine? Let's look at this cosine first. Here we don't have a cosine in front, right? Then we have what? 2 of them, and it's positive. And on the next even one, we have what? 12, and it's negative. And then we have what? 30, and it's positive.
What I'm noticing is that the middle term is being added by 2, so it's like 1. Or,
The middle.
or the sine is.
Are you talking about this one?
Yeah, it's like 4
Okay.
times sine x, and then 6 cosine, and then 8, then 10, and 12. And then the first term is 2 plus 4, then plus 6, then plus 8, then plus 10. I don't know if that's
Yeah.
a pattern.
It's a pattern, for sure. So do you all agree with me right now? It's looking kind of very cumbersome to try and come up with a formula, right? Very cumbersome. So let's do something. I mean, we can start to get lost in patterns here. Let's finish the second part of doing Maclaurin, which is to evaluate this where? At 0, okay? Let's evaluate these at 0 and see what we get. Now, I don't have room on my table to do this, so I'm going to do them in blue. What would happen if I evaluated this at 0? You get 0. Okay, what would happen if I evaluate this one at 0?
0.
Get 0? Okay, what about this one at 0? I don't get 0 this time. I get what?
2.
I get 2 times cosine 0 is 1, and then everything else is 0, isn't it? So I get 2. Right? What's the next one? 0, sine of 0, 0, 0, 0, 0. Everything that has an x in it in the front is going to go away, isn't it, when we do Maclaurin? So 0 here. What's this one? Negative 12. Cosine of 0 is 1. Negative 12. 0, 0, right? What about the next one? 0. What about the next one? 30. Okay, this looks doable, doesn't it? This looks, I mean, at least we have some sort of pattern. Let me list out what these derivatives are. So I'll write it out explicitly. The zeroth derivative at 0 is 0, right? The first derivative at 0 is also 0. The second derivative at 0 is 2. The third derivative at 0 is 0. The fourth derivative at 0 is negative 12, and then 0 again, and then 30. Okay. Got that? Excuse me. Now, I need to erase all this. Sorry. I'm going to do what I did before when we did the sine and cosine. I'm going to try and write out the Maclaurin just one at a time. So letting n be 0, what is the zeroth derivative at 0? 0, right? 0 over 0 factorial x to the 0. Plus, now I take the first derivative at 0, which is 0 again, over 1 factorial x to the 1. Plus, what's my next one? 2 over 2 factorial x squared. Next one. 0 over 3 factorial x to the third. Next one. I'm at 4, right? Negative 12 over 4 factorial x to the fourth. Next one. 0 over 5 factorial x to the fifth. I'm going to go as far as I have information. Plus 30 over 6 factorial x to the sixth. Plus dot, 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 right? Let's kill off everything that's a 0. Gone, 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 gone. I've got 2 over 2 factorial x squared minus 12 over 4 factorial x to the 4th plus 30 over 6 factorial x to the 6th. Those are the first three terms, aren't they? Any guess the next one will probably be minus? So can you get a formula from this? I wonder, do we see anything? Do we see any patterns? How about we do one more thing? Does anyone see a pattern? Try one more thing. What did I do there? 2 over 2 is 1. Okay. How about here? What is 4 factorial for real? 24. What is that? 1/2? So minus 1/2 x to the 4th plus, okay, this is 30 over, this might be easier to see it this way, right? It's 30 over 6 factorial. Pardon me? Oh, yeah. But what is, if this is 6 factorial, right? What's 6 times 5? That's 30, right? So the 30s cancel and you just get 1 over 4 factorial. 4 factorial. Okay. Why did this turn off? Come on, I'm right here. Oh. There we go. Okay, and then it was x to the what? 6th. Let's take a guess as to the next one, because there is a pattern here. Isn't 2 the same as 2 factorial? And isn't this the same as x squared over what factorial? 0 factorial. Why are you saying 0, not 1? The pattern. 0, 2, right? This is going up by 2 each time. So what is our guess as to the next one? Minus, right? 1 over 6 factorial x to the 8th. And that is actually correct. Which, written in sigma notation, it needs to alternate starting positive. The bottom is going to be even numbers, right? Starting with 0, right? So 2n factorial, bless you. 2n factorial. And then what about the powers? They're all even, starting with what, though? 2. So I'm going to do 2n plus 2. There it is. That is your Maclaurin for that. Frickin' yuck, right? That's bad. That's bad, right? Watch this, though. And don't get mad at me. Too late. X squared times cosine x is what we were doing to begin with, right? What's the Maclaurin for cosine? We did that previously. What's the Maclaurin? Sum n equals 0 to infinity, negative 1 to the n, over 2n factorial, x to the 2n.
Okay, I'm mad at you.
Push this in. And what happens? You add 2 to this exponent.
And that's it.
And that's the same answer we just got right here. Right? So what I'm getting at here is to show you that, yes, you can get Maclaurin this way, right? But it wouldn't make sense to do it this way if you're allowed to do this, which we are allowed to do. You can push the variable in here like this. You can do that because x is not impacted by n, right? You can't do anything if there's an n here. You can put numbers and variables can go in here as long as that variable doesn't coincide with the index. So this is what we could have done just to start.
So we can treat the x squared kind of like a constant?
Yeah, just push it in. Yep. Because think about it this way. This is a series, right? If I were to write this series out, it's like something plus something plus something plus something, right? And it goes forever. And in front of it, you have x squared. So what would you do? You would distribute the x squared to each one, right? Well, that's the same thing as just putting an x squared right there. That way that x squared impacts each term. I wanted you to see just how messy things can get when it comes to Maclaurin, right? That's why it's so important to have Maclaurin series for the basic functions. Because then when you start combining them with other functions, you can use them, right? I know the Maclaurin for this, so if I want to know the Maclaurin for this whole thing, I use the cosine's Maclaurin to do that, all right? All right, let's keep going. So the next one, example 7, I'm going to skip, and if I have time at the end, I will do it, all right? So what I want to do now is I want to illustrate what is nice about this. One of the things that's nice is that we can now, equipped with the Maclaurin and Taylor series, we can now evaluate integrals we couldn't do before. And I alluded to this previous class. This right here is an integral we cannot do with any technique that we have, any technique of integration, right? But we know that e to the x is the sum n equals 0 to infinity of 1 over n factorial x to the n, right? We derived that first example I did today, right? That is the Maclaurin series for e to the x. Well, the great, beautiful thing about Maclaurin, one of the great, beautiful things about Maclaurin, is that this can be anything, u. And then you just replace this right here with u. So e to anything is going to be that formula, replace that u in there. So what's another way I could write e to the negative x squared? As the sum, n equals 0 to infinity, of 1 over n factorial, then what? Negative x squared to the n. You see, I'm replacing the negative x squared. That's now my u, right? And I'm going to do a little bit of cleaning up of this. Tell me, hold on. Yes, that was right. Sum n equals 0 to infinity. Okay, I'm going to do something that you had to do if you've been working on that take-home thing. What is negative x squared to the n? How can I rewrite that? That's what we're talking. You can write that as negative 1 times x squared to the n, but that's the same as negative 1 to the n times x squared to the n. I heard that some of y'all were working on this and had a little bit of a disagreement as to what it was. So that's what that is. So I can rewrite this as negative 1 to the n over n factorial, and then x to the 2n, right? So I'm just rewriting that using this. You see?